Hi friends, welcome to this session. So in this lesson, we are going to see the concept partial fraction expansion. This is also from the subject signals and systems, but this is helpful in finding the inverse Laplace transform of the given frequency domain signal. So basically, we find inverse Laplace transform of the given frequency domain signal by using a direct method, which is nothing but the formula method. So by using the formula for finding inverse Laplace transform, we are going to find the time domain function, that is x of t, for the given frequency domain signal. So this is what we do in order to find the inverse Laplace transform. But this process is quite time consuming. So in order to avoid this, what we do is, we are going to use this partial fraction expansion concept to find the inverse Laplace transform of given frequency domain signal. Okay. First of all, what is partial fraction expansion? Partial fraction expansion. So partial fraction expansion is nothing but the method used to decompose or expand or split the given rational expression or fraction into multiple simpler fractions is called as partial fraction expansion method. So the method which we use to decompose or expand or split the given rational expression of fraction into multiple simpler fractions is called as partial fraction expansion method. That means breaking a single fraction into multiple smaller fractions is called as a partial fraction expansion method. Basically, we add or subtract fractions in order to get the single fraction. So till now we have done this. Till now we have done adding or subtracting given fractions in order to get the single fraction. But the reverse of this process, that means splitting the given single fraction into multiple simpler fractions, is the process called as partial fraction expansion method. So let us have a look of this partial fraction expansion with an example. So given fractions are 2 by x plus 2 plus 4 by x minus 1. Here we are asked to add these two given fractions. So 2 into x minus 1 plus 4 into x plus 2 by x plus 2 into x minus 1, that is equals to 2x minus 2 plus 4x plus 8 by x plus 2 into x minus 1, that is equals to 6x plus 6 by x plus 2 into x minus 1. So this is the process of adding. If there is a minus sign over here, we can say that subtracting given fractions to get a single fraction. This is a normal process. But the reverse of this process, that means converting this single fraction to simpler multiple fractions. This process is called as partial fraction expansion. So in this lesson, we are going to learn this process of partial fraction expansion. And this partial fraction expansion can be used only for proper fractions. So, partial fraction expansion process or method can be applied only on proper fractions. And what is a proper fraction? Proper fraction is a fraction in which the degree of numerator is less than the degree of denominator. That means if f of x by g of x is a given fraction, and if the degree of f of x is less than the degree of g of x, then this fraction f of x by g of x is called as a proper fraction. So when the given fraction is a proper fraction, then only this method partial fraction expansion can be applied on it. And what if the given fraction is an improper fraction? Improper fraction is a fraction in which the degree of numerator is greater than degree of denominator. That means if f of x by g of x is the given fraction where f of x and g of x are polynomials, and degree of f of x is greater than degree of g of x, then that type of fraction is called as an improper fraction. When the given fraction is an improper fraction, we can't apply partial fraction expansion method on it, because partial fraction expansions can be only applied for proper fractions. In that case, what we are going to do is we are going to convert this improper fractions to proper fractions. And how we are going to convert this improper fractions to proper fractions? Basically, an improper fraction can be expressed as polynomial in a variable, let us say x, plus partial fraction. So in this way, we can convert the given improper fraction to proper fraction, and this can be done by using long division method. By using the process called long division method, we can convert the given improper fraction to proper fraction. So let us see with an example. So consider f of x is given as 2x cube plus 9x square plus 11x plus 2 by x square plus 4x plus 3. Here degree of numerator is 3 and degree of denominator is 2. Clearly, degree of numerator is greater than degree of denominator, which is nothing but f of x. Given f of x is improper fraction. So now, by applying or by using the long division method, we are going to convert this given improper fraction to proper fraction. So divide 2x cube plus 9x square plus 11x plus 2 by the divisor x square plus 4x plus 3. So x square into 2x is equals to 2x cube plus 4x into 2x is 8x square plus 6x. Now subtract this. So we get x square plus 5x, x square plus 1 is equals to x square plus 4x plus 3. Again subtract this. So we get x minus 1 as the remainder. Now the given f of x equals to 2x cube plus 9x square plus 11x plus 2 by x square plus 4x plus 3 can be expressed as a polynomial in x plus a proper fraction, which is nothing but x minus 1 by x square plus 4x plus 3. Here this polynomial in x is nothing but the quotient, and this is the proper fraction, which is nothing but the remainder by divisor. So in this way we have converted an improper fraction by using the long division method to proper fraction. Now we can apply partial fraction expansion to this proper fraction and get the inverse Laplace transform of the given signal. Now we will see the steps to follow in order to find the partial fraction for the given fraction or given rational expression. First of all, the fraction should be the proper fraction. Then we need to factorize the denominator in the given rational expression or fraction. Then create individual fractions for the given fraction. Individual fractions which are nothing but partial fraction. For the given fraction on the right side, such that each fraction consists each of the factors of the denominator acting as the denominator for the individual fraction with numerator as unknown values. Which are represented by A, B, C, so on. And the next, add the partial fractions on the right side. So after adding the partial fractions, we'll have the denominators on both sides as same. So cancel out the denominators on both sides as they are equal. So after cancelling out the denominators, now substitute the roots of the denominator in the obtained expression in step 4. So after cancelling out the denominators on both sides, we are left with numerator expressions. So by substituting the roots of the denominator in the obtained numerator expressions in step 4, we will be able to find the unknown values of numerator. Even after substituting the roots of the denominator, if we are left with any unknown value, then we need to expand the expression on right side. And after expanding, collect the common terms and compare the coefficients of similar terms or similar powers of x on both sides. So by comparing the coefficients of similar powers of x on both sides, we will get some equations. And in these equations, if we substitute known values of a, b, c, we can obtain the unknown value. So in this way, we can obtain the unknown values of numerators, that is a, b, c, and after finding these values a, b, c, substitute in the partial fractions obtained in the step 2. So in this way, we can generate the partial fractions, or we can decompose the given proper fraction into simpler multiple partial fractions. So the steps to be followed are, first of all, the given fraction should be a proper fraction. If not, convert the improper fraction to proper fraction. Then factorize the denominator. Then create individual fractions, that is partial fractions, in such a way that each factorized denominator acts as a denominator for the individual fraction, with numerator as unknown values which are represented by ABC. And then next step is adding the partial fractions. And after adding the partial fractions, both the denominators on both the sides will be same. So cancel out the denominators on both sides. Then substitute the roots of the denominator in the obtained expression in the step 4. So that we will be able to find the unknown values of numerator. Even after following this step, if we are left with any unknown value, we need to expand the expression on the right side and collect the common terms and compare the coefficients of similar terms or similar powers of x on both sides. By comparing the coefficients of similar powers of x on both sides, we will get some equations. and by substituting the known obtained values of ABC, we can get the unknown value. So in this way, we can obtain the unknown values ABC of the numerators, and after obtaining these unknown values, substitute them in the partial fractions which we obtained in this step 2. So by substituting those unknown values, we can get the partial fractions, which is nothing but we have split the given proper fraction into multiple partial fractions. So these are the steps to follow in order to obtain the partial fractions. So that's it for this lesson. I hope I am clear with my explanation. And in the next lesson, we will see the partial fractions for proper fractions with examples. And there are different cases also. So we will see all those things in next lesson. Till then, have a great day and thank you for watching this lesson.